In today's video, we're going to talk about a special kind of power series called the Taylor and Maclaurin series. So let's see what a Taylor series looks like. So if we have a function f with all of the derivatives exists, at an value x equals a, I can define the Taylor series to be of this form. So you take the derivative of order n, you plug in the value a, you divide by n factorial, and then you multiply by x minus a to the n, and that would be your general form of your Taylor series. So let's expand it. You have f of a, then f of a prime x minus a, so this is the first derivative, this is the zero derivative, then the second derivative you divide by n factor 2 factorial, then you multiply by x minus a squared, and so on up to infinity. So that's the general form of a Taylor series. Now a Taylor series at x equals 0 is a Maclaurin series. So a Maclaurin series is just a special case of your Taylor series. Now the Taylor series for any function is unique. So for example, if you have a certain function and you have a power series representation for that function, then that power series is actually your Taylor series at the point A. So if your function already has a power series, that's already your Taylor series. I can't have multiple Taylor series for different functions. Okay, so that's a Taylor series. How about Taylor polynomials? So a Taylor polynomial is the nth partial sum of your Taylor series. So if you take a certain amount of terms, that would be your Taylor polynomial. So the general form for a Taylor polynomial looks exactly the same as the Taylor series, but we stop at a certain value n. And similarly for a Maclaurin polynomial, it's the same as a Taylor polynomial, but it's at x equals 0. So let's try and evaluate some of the Taylor polynomials and Maclaurin polynomials. So in the first example, I want to find the Taylor polynomials p1, p0, p2, and p3 for the function 1 over x at x equals 1. So the steps here are quite easy. The only thing that I need to find, I want to find the derivatives, plug in the value of your x, which is your a in the definition. You want to plug in the values of a into your derivatives. Once you're done with that, you just construct the polynomial by plugging everything together. So let's see. My function is 1 over x. You can represent this as x to the negative 1. The first derivative is minus x to the negative 2. The second is 2x to the negative 3. Then we have 6x to the negative 4. Now if you plug in the values of your a here into all of these derivatives, so here since I want to find the polynomials from like p0, 1, 2, and 3, I only need the derivatives up to the third derivative. So now let's plug in the values. If you plug in 1 here, you're going to get 1. If you plug in 1 here, you're going to get negative 1/2, 2, sorry, no, negative 1/2, just negative 1, then 2, and 6. I think this is negative, yeah. So negative 6, like that. Now, once we're done evaluating all of the derivatives at that certain point, we're just going to plug in everything and plug it together. So p of 0 is just f of 0. Sorry, not 0. F of 1, because we use the point A. So this is just 1. P of 1 is f of 1 plus f prime of 1 divided by 1 factorial, that's just 1, then x minus 1. So if you plug in the values, that's 1 minus x minus 1. P of 2 is the same exact thing. You take the Taylor polynomial up to the second degree. Then you plug in the values of your derivatives. So 1 minus x minus 1 plus, now f double prime is 2 divided by 2 factorial, that's just 1 multiplied by x minus 1 squared. Now similarly for P3, well, technically P3 is all of this plus the third derivative at 1, 3 factorial x minus 1 cubed. So now these terms are equal to this, so you can just take it down. And then we're going to have, now f triple prime is negative 6. And 3 factorial is 6, so negative 6 divided by 6, that's just minus x minus 1 cubed. Okay, so that's it. That's the Taylor polynomials. Now for B, we want to find the Maclaurin polynomials for f equals sine. Now here, they don't have to give you like the point, because you know that Maclaurin polynomials is always at x equals 0. So here, the function is sine. The first derivative is cosine, then negative sine, negative cosine, and we want to plug in 0. Sine of 0 is 0, 1, 0, and negative 1. Now again, just constructing the values. P of 0 is just f of 0, that's just 0. Then you go up to the first derivative. So that's just x. Then you have up to the second derivative, and don't forget to divide by n factorial, which is 2 factorial here. So that's just x, because the second derivative at 0 is just 0. And similarly for the polynomial of the third degree, you go up to the third derivative. And that would be x minus, so these two terms goes away because it's 0. Then here, this is negative x cubed over 6. So this is the general Taylor and Maclaurin series and their polynomials. It's just a bunch of calculations of finding the derivatives and then plugging in the values. Now let's see how these polynomials could be like helpful. We can use linear and quadratic approximation to estimate values of functions. So for example, let's use the first and second Taylor polynomials of the function radical x at x equals 4 to estimate the value of the radical 6, because I can't find the value directly because it's not a perfect square. So let's see how that helps. So to find the first and second Taylor polynomial, we need to find the first and second derivative and then plug in 4. So if that's your f, that would be your first derivative, then try it. You'll find that this is your second derivative. Once you plug in 4 inside of these derivatives, you're going to get these values. Now let's construct the first Taylor polynomial. So we're going to have f of 4 plus the first derivative okay, I think I made a mistake here, so let me actually redo it. So yeah, let's see. We have the f of 4, then the first derivative x minus 4 plus, oh, we're going to stop here since this is first polynomial. Now for the second polynomial, we're going to have the same exact thing as the first polynomial, and then we're adding the second derivative divided by 2 factorial, x minus 2, x minus 4 squared. If you simplify, you should get this. Now to estimate the radical here, we're just going to plug in the value 6 inside of your polynomial. So if we want to approximate the radical 6 by the first Taylor polynomial, I'm just going to plug in 6 there. So that's 2 plus 4, 6 minus 4. So that's 2 plus 1/2, which is equal to 2.5. If we use the second Taylor polynomial, we're going to have, now for this part here, we already know that this is equal to 2.5 minus 1 over 64. So that's 2.5 minus 1 over 16. And if you approximate that, you're going to get 2.44. So if you take the square root of 6 in a calculator, you'll see that this is a very, very close-up estimation. Now let's use the fourth Maclaurin polynomial to approximate cosine pi over 12. So again, we're going to find the derivatives, the first 4 derivatives. You're going to get all of these. Once you plug in 0 there, since we're doing a Maclaurin's polynomial, you're going to get 1, 0, negative 1, 0, and 1. And then we're going to take the fourth polynomial, and that would be f of 0, which is 1. Then the first derivative is 0, so there is no term there. Then the second derivative is negative, so that's negative x squared over 2. Third is 0, so it disappears, and then plus x to the 4 over 4 factorial, which is 24. Now if we plug in, if we want to estimate cosine using that polynomial, we're just going to plug in pi over 4, pi over 12 in there. So that's 1 minus pi over 12 squared plus 1 over 24 pi over 12 to the 4th. So that's it. It's all about calculating the derivatives and plugging in values and getting the polynomials. Now, if we want to represent functions in terms of Taylor and Maclaurin series, the most difficult part here is I want to find the nth derivative for my function. I want to find the general form or the general formula for that nth derivative. Once I'm able to find the nth derivative, I can just plug it into the formula of the Taylor series, which is this one here. And I can write any functions in terms of that. So the main goal here is if you're able to calculate the nth derivative, or you're able to find that formula, you just plug it into this series and you're done. Let's try this example. I want to find the Taylor series for this function here at x equals 2. Oops. For this function at x equals 2. If we want to find Taylor series, we immediately start finding derivatives. You take the derivatives until the 4th, 5th, until you can see a pattern, and then you can generalize for the nth derivative. So let's start. I can rewrite my f of x as x to the negative 1 over 2. Then the first derivative is minus x to the negative 2 over 2. The second derivative is 2x to the negative 3 over 2. Then 2 multiplied by negative 3, x to the negative 4 over 2. Then 2 times 3 times 4, because negative times a negative goes away, over 2. So here, I like to keep the numbers by themselves and not multiply them. That way I can notice patterns easier. So for example here, the reason why I left them without I did not multiply them, because if you can tell, this kind of looks like a factorial. So it would be easier for me to determine whether I have a factorial or I have like a multiple of certain stuff, and I can generalize it when we have it for n. Okay, so you always start you always like find the nth derivative, always start by looking at like, oh, do I have an alternating signs? Do I have it like positive, negative, positive, negative? If that's the case, then that's the first thing that you should add. I have -1. Is it to the n or to the n plus 1? So let's see. The first derivative was negative. The second was positive, then negative, then positive. So all of the even terms are positive and all of the odds are negative, so I can just take it to the n. Perfect. Now, the second easiest thing that I can see here, all of the derivative, they have 2 in the denominator. So I must have 2 in my denominator. Then the second easiest thing here is I have x to a certain exponent. Is it the same degree as my derivative, or is it bigger? Is it lower? Let's see. When I had the first derivative, I got an exponent of 2. Don't mind the negative. I can take it to the denominator. That's not a problem. When it was a second derivative, I got 3. So if you can see, I'm raising the exponent to the same degree of the derivative added, but like I have a plus 1. So I'm going to have x n plus 1. And I took it to the denominator to make it positive. And then the last thing, I have the numbers. So I have 1, then 2 times 1, then 3 times 2 times 1. Here I have 4 times 3 times 2 times 1. So here, this is definitely a factorial. Is it the same degree? Is it bigger? Is it lower? Let's see. Fourth derivative, I have a 4. Third derivative, I have a 3, which means I have the same value, which is n factorial. So that would be my nth derivative. So that's it. You just take your nth derivative, you plug it at the value that you want to like evaluate your Taylor series at, which is 2. You just plug it into your nth derivative, and that would be your general form for the Taylor series. So your function is going to be equal to the nth derivative at 2. So I'm just going to plug in 2 instead of x. And then we need to divide by n factorial. So I just divide it like that. X minus 2 to the n. So let's simplify. These goes away. And I have 2 and 2 to the n. I can combine them into 2 plus 2 to the n plus 2, x minus 2 to the n. So that's the Taylor series for my function. Now let's find the interval of convergence. I'm going to use the ratio test here. So an over an plus 1 over an. So that would be these. And we can simplify them easy. I'm going to have x minus 2 with an absolute value. And then the negatives goes away, and I have an absolute value, so it goes away for sure. And then I'm going to have a 2 in the denominator. These go away, so I just have an extra 2. So since I'm using the ratio test, for this to converge, it has to be less than 1. If we cross multiply, we're going to get this. Now, if you use properties of absolute values, you're going to have this. If you solve it, it's between 0 and 4. So we know for now the interval of convergence is 0 and 4. But are the endpoints 0 and 4 included in the interval of convergence? Here we need to test each point separately. So when x was 0, you just plug it into your original series. Once you plug in 0 here, you're going to get negative 2 to the n. Now let's simplify. You have a negative and a negative, so that would be positive, that goes away. Then you are going to have like 2 to the n divided by 2 to the n plus 2, so that's just 1 over 2 squared, which is 4. Now this diverges. And you can test, you can check. Similarly, when you plug in 4, once you plug in 4 here, you're going to get 2 to the n. So we're going to have negative 1 to the n over 4. And this also diverges. Which means that the interval of convergence is just from 0 to 4 open. If one of these were convergent, then you have to put like a closed parenthesis here. Now let's find the Maclaurin series for my function e to the x, and we want to determine the interval of convergence too. You want to find a Maclaurin series or a Taylor series, you start by finding the derivatives, and then generalize to find the nth derivative, and then plug in the values. So let's see. If you keep finding the derivative of e to the x, it's just e to the x multiple times, which means that my nth derivative is also e to the x. Now, my nth derivative is e to the x, and I'm finding a Maclaurin series, so my a is, or like you need to find it at x equals 0. So I'm going to plug in 0 here. Once you plug in 0, that's just 1. So if you want to find the general form for your function, it's going to be the nth derivative at 0 divided by n factorial x to the n. So that's 1 over n factorial x to the n equals 0 to infinity. So that's your Maclaurin series for your function. If we want to find the interval of convergence, let's take the ratio test by taking the limit. So x n plus 1 over n plus 1 factorial multiplied by n factorial over x to the n. If you simplify, you're going to get the absolute value of x, 1 over n plus 1, as n goes to infinity. And this is 0. Now, this is 0 for all values of x, which means that the series converges for all values of x. So the interval of convergence is from negative infinity up to infinity. So these are the main ideas of the Taylor and Maclaurin series. It's really simple. It's just the general form for the Taylor series and finding the derivatives, finding the general formula, and so on. You can do these problems if you want to have extra practice. And if you have any questions, please let me know. If you need office hours or need anything, just email me, and best of luck.